Hello, welcome to the Bakwas channel for self-paced tutorials on Internet of Things. This video demonstrates how easy it is to count objects using YOLO 11. This feature has dramatically accelerated the ease in using vision processing for common activities at work and home. This presentation is nostalgic for me personally. In college, when the Beatles were still together as a band, our class visited a large railway workshop close to the campus. We saw some automated marshalling of wagons in action. I always wondered why we couldn't use a camera to look at the wagons and direct them to the right track. Of course, there are many other business requirements, but my primary thought was to avoid installing special scanners along the tracks to read codes on the side of the wagons for the marshalling. That was decades before the advent of digital cameras, but we had already studied in class how charge-coupled devices, CCD, would revolutionize vision processing. The other kid-like exercise was to count the number of wagons passing along a railway track and to keep a mental note of when to avoid the crossing at the perimeter of the campus. Our destination for the break was a watering hole, a tea only of course, a no-frills shop across the tracks, and the idea of waiting for several minutes at the railway crossing didn't suit our impatience. And this used to be around midnight. You get the idea. Of course, there are many more youthful stories that I could bore you with, but the key theme is that what you dreamed a few decades ago is reality today. That is the march of technology. NVIDIA is living proof of that trend. Ask anyone who attended the first SIGGRAPH conference in the early 70s when parallel processing and graphics coprocessors were in their infancy. We've covered the basics of counting in YOLO in previous tutorials, but please bear with me as I rehash those principles for this presentation. Object counting using deep learning models has a wide range of applications across various industries. In manufacturing and logistics, for inventory management, accurately count items in warehouses, on shelves, or moving along conveyor belts. This helps optimize stock levels, prevent shortages, and improve order fulfillment. For production monitoring, count products during manufacturing processes to ensure quality control and identify bottlenecks in production lines. For quality control, detect and count products or anomalies in processes. In retail, for customer counting, count customer movements in stores to analyze patterns to optimize staffing. For shelf monitoring, detect empty shelves and racks for replenishment. In traffic monitoring, for vehicle and pedestrian movements. In agriculture, for crop counting and pest detection. In security, for crowd counting and object tracking. In environmental monitoring, for wildlife counting and pollution monitoring. Some of the advantages of object counting are described by Ultralytics at their website. Allow me to repeat those points here. In resource optimization, object counting helps with efficient management by providing accurate counts and optimizing resource allocation in applications like inventory management. In enhanced security, object counting enhances surveillance by counting and tracking moving entities. In informed decision making, object counting generates data for use in optimizing processes. The key entity for counting objects is object counter. The key fields are model, which is the path to the model file, region, a list of points defining the counting region of interest, show, a Boolean flag to control the display of the video stream. Some of the other parameters are show in, a Boolean flag to display the counts of objects entering the region, show out, Boolean flag to display the counts of objects leaving the region, line width, line thickness for the bounding boxes. We will visit the full Python script in a moment, but for now, just let's go through quickly the use of object counter in our code. And it's in this section where we use object counter. And as the attributes have been explained in the slide, we have a model name, we have a region of points that we define. So we have a model name, and then we have a region of points that we have to experimentally figure out what's best. We want to see the video stream on the screen, and obviously we want to see the counts, how many coming in and how many leaving. The region is defined by a box. It can be a rectangle or it could be a polygon, depending on the number of points you specify, and the thickness of that region is defined by this parameter line width. The model track parameters control how the model performs object tracking in videos or image sequences. Source specifies the source directory for images or videos. It supports file paths and URLs. Persist enables persistent tracking of objects between frames, maintaining IDs across video sequences. Tracker, which is a string, specifies the tracking algorithm to use. Conf sets the confidence threshold for detections. Lower values allow more objects to be tracked, but may include false positives. Intersection over union, IOU, sets the intersection over union threshold for filtering overlapping detections. Classes filters results by class index. For example, classes with 7 and 8 in the list only tracks trains and suitcases. Verbose controls the display of tracking results, providing a visual output of tracked objects. By adjusting these parameters, one can fine-tune the tracking behavior to suit specific requirements, such as improving tracking accuracy, increase IOU threshold for stricter association between detections, filtering out false positives, increase the conf threshold to only track highly confident detections. Focusing on specific objects, use the classes parameter to track only objects of interest. Of course, a lot depends on the chosen model too. visualizing tracking results. Enable these to review the tracking performance. You will inevitably have to refine your parameters iteratively and select an appropriate model to use the results productively. The demonstration uses the basic YOLO 11 pre-trained model for the COCO dataset, excluding the experiment or X model. The models have the object of interest classified as train. No further training nor any transfer learning was performed since I had only a few video streams to test for the purpose. Remember that all model building requires 3 sets of data: training, testing, and validation. For this tutorial, no attempt was made to refine the model with the transfer learning process that is recommended presently for deep learning model development. In the near future, I hope to be able to capture some more videos for future tutorials on object cropping and counting in regions. Since there are 4 models, the result from each model will be displayed in a quadrant. Of course, to set the scene, the original source image will be displayed by itself prior to the comparative display. I would like you to focus on the principles and concepts and not the detailed results. You will see that YOLO 11 makes it very simple to dip your toes in the water. I have tweaked the original Ultralytics sample Python script to make it just a little more general purpose. Let's step through the Python script that we're going to be using for this demonstration. So after the comments are over, we're importing the Ultralytics package, and we're of course going to be needing the help of OpenCV to stream the video in. We've, through experiments, established a suitable region, and this is a rectangle rather than a polygon, and we're going to be looking for trains. The model, initially we start off with 11N, the nano, and then we'll step our way through small, medium, and large. And here I'm specifying the source for the video. It's in the local folder, and we start off by using OpenCV video capture for the video source. So we tell OpenCV to go ahead and read the video stream, and then frame by frame we will go ahead and process it. So before we can do that, as we have witnessed before, we will go through and define the object counter parameters so that it makes us a little better and efficient in processing the frames. We do have model track that we had mentioned in the slides before, and here we have tracks, and we will persist it and show it. So essentially what we do is frame by frame, we will read the video stream and process it and count it and then submit the results. So that's a very simple script. It's direct from the Ultralytics site, and I hope that you feel empowered to go ahead and run it. So to run it, all we do is click on run, and then it'll run. I still haven't purchased the 16 gigabyte Raspberry Pi 5 board. With so many boards lying around in my study, I really need to focus on helping you to hit the ground running rather than buying new toys. So the demonstration was run on an 8 gig Raspberry Pi 5 board that uses an SSD card. There is an additional M.2 slot free that hopefully I will use for a CUDA AI card, whatever that means, when the prices decline just a little bit more. For software, all you need is the Ultralytics package, which PyCharm will download and install for you in the recommended virtual environment. For most of my work on Raspberry Pi, I prefer to stick with the Foundation's version of Debian operating system. Of course, I do have other operating systems running on various models of the board, but that topic is out of scope for now. As you can see from my summary, it is very easy for you to get started if you are accustomed to headless mode of operation. Incidentally, the same Python script was run on the DF Robot RDK X3 single board computer too. Of course, it ran very slow there. So what are you waiting for? Get rolling as soon as you can. There are very significant changes occurring in the AI world. Don't be a bystander. Seismic change would not be a hyperbole here. The pace of changes makes it very difficult to stay afloat. You have to swim as best as you can. Participate to the extent you can. Then you will have to learn more techniques if you wish to migrate to generative AI. Before we run the Python script, let us examine a few key sections in the code. The process is essentially the classic input, process, output paradigm. Naturally, the Ultralytics package permits this simple linear process flow. Remember, we can use a diverse variety of input sources to feed the inference engine, ranging from images to video. The latter can be recorded files, direct feed from a camera, or streamed from the internet. Ultralytics really does take care of enabling the input to the inference engine. While there are many items of interest that are output by the script during the runs, the main focus for this tutorial is naturally on the counting of classes or objects in the input. The Python script was run on a Raspberry Pi 5 and a DF Robot RDKX3 computers. Naturally, we cannot pretend that these single-board computers are comparable to desktops where perhaps CUDA from the graphics card provides an added advantage. So let us just focus on the summary results only for now. The four pre-trained models are nano, small, medium, and large. I've excluded the research or X model in this set of runs. Again, this tutorial is not the place to evaluate a truth table, but it is extremely exciting to see that all models were in the ballpark for this given source stream of a highway and a railroad track where objects were in motion. The nano model didn't detect the trains, but the cars and trucks were consistent across all models. While it is tempting to use the pre-trained model as is, I would strongly advise against it. We should always try our best to train our own model using transfer learning from the YOLO pre-trained models. I have a tutorial under preparation just to illustrate this process. This short tutorial demonstrated the counting of dynamic objects in a video stream using the Ultralytics YOLO 11 package. The demonstration leveraged starter Python script provided by Ultralytics. There are many options to tweak the script to suit one's requirements and preferences. There are many applications of this solution. Go ahead and test a similar script in your own environment. You've always wanted to perform live inference without slinging code, correct? Ultralytics has you covered with their Streamlit solution. Install the Ultralytics package and then run the command YOLO space streamlit-predict. You receive 3 URLs. Choose one and start the live inference using your preferred source, webcam, or stored files. In this demonstration, I chose localhost on port 8051, and away we went without writing a single line of code. To launch the Streamlit application, ensure that you're in the terminal mode, and go ahead and come back here, and then type YOLO Streamlit predict. And the system will take a few seconds and come back with 3 URLs. The first URL is the localhost, and that would be our preferred option since we're going to be running it on the same desktop. The second one will allow anybody in the network who has access to the desktop to launch that. And the third one is for an internet connection that's really not advisable because of the unnecessary infrastructure changes that you may have to make for port-to-port routing. So we'll stick to localhost and make a note of the port number, which is 8501. So by clicking on localhost, we were able to launch the Streamlit UI. And you can see in the left nav bar, there are a bunch of user options that I'd like to change some of them. First of all, we're going to use a video, not a webcam. And so it's asking us to drag and drop a file. And I have one conveniently available, so I'll just drag and drop it in there. And then in terms of classes, what I'd like to do is just use the ones that we know exist. So cars, trucks, and trains. So let me go ahead and pick train, and then we'll pick truck also. So I've got those 3 in there, and now all we have to do is start the processing. So if I scroll up a little bit here on this side, and we'll stick to the YOLO 11 nano model, and let's go ahead, and you can see the confirmation message, the model has been loaded. So we click on the start button. And it's going to start processing very shortly. The video will come up, the first frame, and thereafter it'll stagger its way through the entire video sequence. So the original video is on the left, and the frame on the right is the live inference that is being done by YOLO. So I'm not going to go and bore you through the entire sequence. I just wanted to give you a quick idea of how side by side you can see the original video and the results without writing a single line of code. And you have the flexibility of choosing different classes that you want to detect. You can choose the model, and naturally, of course, there are some threshold values for confidence and IOU that I discussed in the tutorial that you can tweak to see what you're getting from the results. So once again, I hope that this introduction to no-code inference detection using Ultralytics YOLO Streamlit is helpful for you, because it'll give you the confidence to test your models and not have to worry about writing Python or C++ or even command line interference for that matter. So have at it and go ahead and experiment. There's no charge for this. It's available on the web at no cost to you. That's all, folks. Thanks for taking the time to view this presentation. Would love to hear from you with your feedback. You're always welcome to be critical in any which way you can. Until next time, bye for now. This presentation was prepared with assistance using free open source software, FOSS, from Ultralytics for YOLO, JetBrains for PyCharm Community Edition, Python Communities for all supporting packages, and of course for the preparation of this tutorial from OBS Studio, Kdenlive, LibreOffice, and of course Ubuntu. Teachers, viewers, and peers provided valuable feedback. My apologies if I have inadvertently omitted anyone from this acknowledgement. A very big thank you to y'all for the assistance.